Welcome back to ICFP 2020, where the next paper is going to be Effects for Efficiency, Asymptotic Speed Up with First Class Control, and it's going to be presented by Daniel Hillestrom.
Hi, my name is Daniel Hillestrom, and I would like to tell you about some recent work I've done with Sam Lindley and John Longley on how the presence of first-class control in a language can speed up implementations of some programs. I'll dive right in. The purpose of this work is really to explore space. The space I have in mind here is the design space of programming languages. When studying the expressiveness of some language feature, like first-class control, it is customary to consider a language with the said feature, and then the fragment modulo that feature. Then we can pose questions along different dimensions such as computability, complexity, and programmability. However, any such question is really only interesting if the setting involves higher types, because to a fair approximation we can regard all reasonable languages with first order types as being equi-expressive. So, in this work we are in the realm of higher types, and we show that in this realm the presence of first-class control can improve the asymptotic runtime of some programs. To show this, we consider the generic count problem, which asks us to implement a third order function satisfying this type signature. Let's unpack the type. The first order function parameter is called a point. It is a functional representation of a Boolean valued vector of size n. The second order parameter is a predicate function, which operates on points. It is an encoding of some search problem, and it yields true or false depending on whether it is satisfied by its provided point. Finally, any faithful implementation of this type signature ultimately returns the number of points satisfying a given predicate, or in other words, it counts the number of times a given predicate returns true. We fix our base language to be simply typed PCF and extend it with effect handlers. Our concrete choice of control operator is not essential. Any first-class control operator will do, however, effect handlers do provide a particularly structured form of delimited control, which makes them convenient for the purpose of this work. Then we first show that there exists an implementation of the generic count in PCF with effect handlers, whose asymptotic worst-case runtime behavior is 2 to the n. Then we show that every implementation of generic count in pure PCF has at least asymptotic runtime behavior n2 to the n. That is to say, there exists a strict asymptotic efficiency gap between PCF and PCF with effect handlers due to the presence of first-class control in the latter. In this talk, I will not provide you with the actual proof of this. Instead, I will aim to give you the intuition for why this result is true. I will elaborate a bit on our methodology. We impose one important rule, namely that the type signature of generic count is fixed. That is, no implementation in PCF or PCF with effect handlers is allowed to change the type signature of generic count. A consequence of this rule is that it's not possible to translate PCF with effect handlers into PCF, say by way of an interpreter or CPS translation. This way, we really get to study the essence of the power provided by effect handlers. Moreover, this rule is also reminiscent of the restriction that programmers are faced by every day when they program against an interface, so we do consider this to be a reasonable rule. With this in mind, let's look at the following example predicate called EX and its induced computation tree model. The predicate takes a point as input and applies this point to 0 or queries the 0th component of the point. This is reflected in the tree model by the first interior node, which reads $0. I'm using the question mark prefix here to denote invocations or queries of points, and I'm using an exclamation mark prefix to denote answers or return values of predicates. Now note how the structure of the computation tree coincides with all the possible control flows of the predicate. Let's consider a concrete evaluation of this predicate. Suppose we apply it to a point whose 0th component is true, first component is false, and second component is true. Evaluation begins in the predicate and eventually occurs the 0th component of the point, which is true, meaning that we will take the left branch down the tree. This corresponds to continue with evaluation of the then branch in the predicate. Eventually, the predicate will query the first component of the point, which is false, meaning we will take the right branch down the tree. And then, at some point, the predicate will query the second component, which is true, meaning that we take the left branch down the tree, and we now hit a leaf node with the answer true, meaning that for this particular point, the predicate will yield the answer true. Now, this particular predicate belongs to a certain class of predicates that emit canonical models. We call such predicates instandard. A tree model is instandard if it is a perfect binary tree of height n. In addition, we also require that the tree contains every query and that no subtree repeats any query. We say that a predicate is instandard if its model is instandard. For example, the predicate EX is 3 standard. For the initial analysis, we restrict our attention to instandard predicates. This restriction serves to simplify the analysis, but it also provides us with an instance where the efficiency gap between PCF and PCF with effect handlers manifests as clearly as possible. This restriction enables us to give a crisp implementation of generic count with effect handlers. Okay, let's consider how one might go about and implement generic count with effect handlers. First, we need to take the predicate as input, and we have to apply this predicate to a point. We represent this point as the invocation of an abstract operation called branch. The only thing we know about branch is that it's going to ultimately return a Boolean value. In order to give an interpretation of branch, we must wrap the entire computation in a handler. A handler consists of 2 parts: a value clause that tells us what to do with the return value or the answer of a predicate. So if the answer is true, then we're going to return 1, and if the answer is false, we're going to return 0. Then the second part is an operation clause, specifically a clause for the branch operation, which in addition to giving access to the payload, also gives access to the continuation of the branch operation inside the predicate computation. This is a first-class entity, and what we do is we invoke the continuation with true first, and then we invoke it with false subsequently, and we sum up the result of those 2 invocations. Now, let's consider a concrete evaluation of fcount applied to our example predicate. The first thing that happens is the predicate queries the CUF component of the point. This query causes an invocation of the branch operation. This invocation causes control to transfer into the branch clause in the handler, where the first thing we do is we resume the continuation with true, meaning that we descend down the left branch in the tree. Now, when the predicate queries the first component of the point, the very same thing will happen. Another invocation of branch will occur, causing control to flow into the branch clause in the handler, where we resume the continuation with true, so we descend down the left branch again. We repeat the same argument when the predicate queries the second component, so we descend down the left branch. Now we find ourselves at a leaf node, meaning that we invoke the value clause in the handler with the answer false, meaning that we return a 0. At this stage, the handler is going to backtrack to the most recent query and apply the continuation to false, taking us down the right branch in the tree. Now we find ourselves again at the leaf node, so we're going to invoke the value clause, but this time with the answer true, meaning that we'll return a 1. The handler is now going to sum up the answers that it got in this subtree, which is 1, and then it's going to backtrack to the most recent query, and then the pattern repeats, so it's going to resume the continuation with false and then subsequently with true. So, backtracking here ensures that every edge in the computation tree model is being visited exactly once. So if you generalize a bit, this means that computation involves big O of 2 to the n steps. Now, in PCF without effect handlers, there is no mechanism for backtracking of a sharing computation. Therefore, every generic count function must restart computation for every point. Let me try to illustrate what this means. Let's consider some generic count function applied to our example predicate. And let's for simplicity assume that this generic count function visits the nodes in the computation tree in depth first order. The first thing that happens is that the predicate queries the CUF component of the point, which returns true, meaning that we descend down the left branch in the tree. The same thing happens for the first component and the second component. And so we find ourselves at the first leaf. From here, there is no quick way to get to the second leaf, because there is no backtracking or any means for sharing computation. So the generic count function has to go all the way back up and construct a second point that represents the path to the second leaf, meaning that we'll have to repeat some work along the way in order to finally arrive at the second leaf. And here the situation is the same. In order to get to the third leaf, we must go all the way back up, construct a third point that represents the path to the third leaf, repeating work along the way in order to finally arrive at the third leaf. In general, the generic count function will have to construct endpoints in order to visit each of the leaves. This means that computation involves at least n2 to the n steps. Some might object to PCF as a choice of base language, because it lacks characteristic features found in, say, industrial strength languages. However, as we show in the paper, the efficiency gap remains even under extensions to PCF. Specifically, we consider adding mutable state and exceptions into the picture. We consider them separately and together, and I would claim that once we view them together, our base language forms the prototypical core of an industrial strength language like OCaml or Java. Furthermore, in the paper we also discuss how to relax the in-standard restriction. That is, so the predicate models no longer need to be perfect binary trees, and we can account for repeated queries, and we don't even need to query all the components of a point. We also consider how to extend the problem to search. That is, instead of returning the number of times the predicate was satisfied, return the points that satisfied the predicate. And we show that the same asymptotic bounds applies to the search problem. We also conduct an empirical evaluation. In summary, the takeaway is that control operators admit asymptotically more efficient implementations of some programs. And the intuition for why that is true is because control operators enable computation to be shared via backtracking. And as for future work, we would like to consider how linear handlers fits into the picture. So linear handlers are a special form of handlers that only allow the continuation to be invoked once. It is not clear that our current proof techniques would adapt readily to the situation with linear handlers, so it would be interesting to investigate. Another thing that would be interesting to investigate would be a richer type system, say one that features effect typing, and how that would impact the result. Thank you for tuning into my talk, and thank you for your attention.
Right, so thank you, Daniel. If you want to join the authors for a live Q&A, again, you can just click on the link in the Slido room.